Learning Docker as a beginner can be confusing. I remember my first encounter, which left me completely lost. But after using Docker for over 5 years now, I've discovered an unexpected truth. It's actually pretty simple once you understand the fundamentals. And today, I'm going to break down the core principles that you need to know about Docker in 7 simple steps. And by the end of this video, you'll have the confidence to start building with Docker right away, even if you're starting from scratch. But first, you have to understand the problem that Docker was designed to solve. So, software development can be broken down into 5 simple steps: development, testing, integration, deployment, and monitoring. When I first started in tech, these steps were handled by different teams. Developers would write a code and then throw it over the wall to the operational teams. Now, the ops teams would then be responsible for deploying and maintaining the software, often with little understanding of how it was built. This approach created significant problems. Operational teams would struggle with deployment issues that developers didn't anticipate, leading to delays and lots of frustrations. But today's world is different. With modern DevOps, software engineers are now responsible for the entire lifecycle of their applications, from writing the initial code all the way through to deployment in the cloud. This means software engineers need to understand not just programming, but also how applications are packaged, deployed, and run in production environments. They need to make sure that applications work consistently across all of the different environments, from development to QA to production. This led to a fundamental problem in software development, the one that Docker fixed, which is though it works on my machine problem. You create a program on your computer and it works perfectly. But when someone else tries to run the exact same program on their computer, it doesn't work. This problem happens because the environments, i.e. the specific conditions on each computer, are different. This is because each computer has small differences, maybe a different operating system or different versions of supporting software. And these small differences can lead to errors that can take hours, if not days, to identify and then fix. And it's not just other computers that cause these problems. Your own computer changes over time. For example, you might install a newer version of a programming language for another project, and suddenly your original application stopped working correctly. So, how do we solve this? We need consistent, reproducible environments to decrease the errors. If only there was something that would allow us to package the whole application into a single file, then we could avoid most of these problems. Well, funnily enough, that's where Docker comes in with its containerization approach. Now, the main idea behind Docker is simple. Package everything your program needs to run into one standardized unit called a container. This container can then run consistently on any computer that has Docker installed. Docker gives each application its own isolated environment while it's still sharing the resources with the host computer. This means you don't need to duplicate an entire operating system as you would with a virtual machine, which we'll explain in just a moment, but you still avoid the problems caused by different local installations. Can you see how with this consistent approach to packaging and deploying from the very beginning, it allows developers to focus more on creating new features instead of fixing environmental problems? Now, to really understand why Docker is so important, we have to cover the differences between containers and virtual machines. So, just take a moment and think of a regular computer. Let's say a MacBook, because every good engineer uses a MacBook. The MacBook has hardware, i.e. the physical parts, and software, the programs. Now, a virtual machine is like having a complete separate computer inside of your MacBook. It's created by special software that tricks the virtual machine into thinking that it has its own processor, memory, and storage. Now, in comparison, containers are more like sealed packages that hold programs. Containers share the operating system like the Mac OS, but they only contain the specific extra parts a program needs to run. They use up way less space and start up very quickly. But you're probably asking, why does this even matter? Well, virtual machines form the backbone of cloud computing. When you're renting computing power from AWS, you are using virtual machines. Containers then just run on top of the existing operating system within those virtual machines, making them fast to deploy and more resource efficient for running multiple applications. And businesses use both. Virtual machines provide a secure foundation in the cloud, while containers help manage the applications that run on them. Containers became popular because they let you run more programs on the same hardware while keeping them separate from each other. And this makes it easier to develop, test, and run software software without needing lots of expensive computers. Now, as a modern engineer, you're now expected to understand how your applications will run in these cloud environments. And Docker helps bridge this gap. The same container that runs on your local machine will run identically in the cloud. This consistency makes it much easier to deploy applications to production environments. So the question is, how is Docker able to achieve this? Well, it relies on two primary concepts: images and containers. An image is a file that describes everything needed to run your application. And at its most basic level, it specifies the operating system, components, and libraries that your code depends on. Now, on top of that, it includes the code itself, any necessary configuration, and potentially even environment variables. Now, the crucial detail is that an image is read-only, meaning once you've defined it, the image doesn't change. And this is what keeps your application set up consistent. Any system that can run Docker can download that image and know with certainty it's the same environment that you originally built. Now, to actually build an image, you have to write a Docker file, a text file where you outline the steps to install software and copy in your application. And you might start from a base layer, some lightweight Linux distribution, and then add language runtimes, libraries, and your source code. Docker then runs through these instructions and then packages them into an image. And if you modify something in your Docker file, Docker only rebuilds the layers that have changed, making development faster over time. Now, once you have an image, you can create a container. A container is essentially just an image in motion. It's a running instance of that environment, complete with processes, file systems, and network settings that are separate from the host machine. This isolation prevents libraries and configurations from clashing from anything else running on the host, because a container is ephemeral. When you stop or remove it, it disappears. This encourages the mindset of treating servers as disposable. And if a container breaks, or if you need a fresh start, you discard it and spin up a new one from the exact same image. And the way I see it, ephemeral containers are more than just a convenience. It represents a shift towards a more agile way of thinking about infrastructure. When I'm working with my clients, this agile way of thinking drastically reduces their downtime. Instead of logging into servers to diagnose complicated issues, they treat containers as temporary processes that can be replaced in seconds. Now, another thing, using Docker images and containers also makes sharing simple. You can push an image to a registry, which is an online repository specifically designed to store Docker images. Public registries like Docker Hub host thousands of popular images, while private registries serve enterprise needs. In either case, a developer on another team or a server in a distant data center can pull the same image. And this provides a level of reproducibility that was really hard to achieve with older methods. Now, of course, packaging up software is only half of the story. What if the software you package has hidden security flaws? Can we trust what we are putting inside of our containers? Well, 87% of container images contain at least one high or critical vulnerability. And think about what this means in practice. If you include a piece of software with a security flaw in your container, that same flaw gets copied into every container that you create. So if you're running thousands of these containers across different machines, you can see the problem that arises. And that's where Docker Scout is so critical in solving this exact problem. It's a security scanner that looks at everything inside of your container image and checks it against a list of known security problems. And the great thing is that this scanning can happen right on your laptop while you're developing, or it can be set up to run automatically whenever you build a new container. And if Docker Scout finds something risky, it can stop that container from ever making it to your production environment in front of live customers. And the way I see it, checking for security issues earlier on in the development process just makes total sense. We have to implement security from the beginning. And that's how I advise my clients who are new to Docker, because it's so much easier to fix a security problem during development than after your application is already running in production, because the impact in production is way higher. For development teams working together on projects, Docker Scout adds another layer of confidence because the whole team knows that containers have been checked for security issues. And this is especially important if you're working in industries with strict regulations like banking or healthcare. But honestly, every dev team benefits from catching potential problems early. But what happens when a single container isn't enough? Because a single application might have just one container, but most real-world applications rely on multiple services. You might have a backend service for APIs, a database for storing data, and another container for caching, and perhaps an additional process to handle background jobs. This creates a new challenge. Managing each of these containers independently requires multiple commands, one to start the database, another one for the API server, and yet another for caching the service, and so on. You need to remember the exact sequence to ensure they're connected properly and managing them all separately. And this quickly becomes increasingly difficult and, to be honest, just isn't feasible as your applications start to grow. But don't worry, Docker created a solution for this as well with Docker Compose. It's a tool that allows you to coordinate all of these containers in a single configuration file. In a Compose file, you can declare each service. You specify where the image comes from, how the service should be networked, any volume it needs, and what environment variables apply. Then you can bring everything online with a single command. Docker Compose ensures containers launch in the correct order and can see each other through a shared virtual network if required. From my experience, Docker Compose helps to unify your understanding of the application's architecture because all of the services and their connections were documented in a single file. This clarity is invaluable when you're working in a big development team and trying to ramp up the test environment quickly. Yet, even Docker Compose has limitations when your system grows large. As your user base grows, you might need dozens or hundreds of instances of your containers running simultaneously across multiple servers. And you're probably wondering, why is this a problem? Well, remember, we're deploying to the cloud, so we'll need to know which server has capacity for new containers. What if one container crashes? What if we need to update all of the containers? We're having to take down the application for our users. As a business, you can't afford to have downtime. So that's where container orchestration comes in. Now, that might sound a little bit scary and a little bit of a mouthful, but it's really not. Essentially, it's just an automated system that handles the end-to-end management of your containers. And think about it like this. If containers are your application's building blocks, orchestration is the system that decides where to place those blocks, monitors their health, replaces them when they break, and makes sure that they can all talk to each other correctly. And without orchestration, you would need a team of engineers manually monitoring dashboards 24/7, constantly moving containers around, and handling deployments. And when you consider that Google run 2 billion containers every week for search, maps, and Gmail, you can see why container orchestration is actually very important. And funnily enough, Kubernetes, the most popular container orchestration platform today, was created by Google. But here is the thing. While Kubernetes is viewed as the holy grail, for most small to medium-sized businesses, Kubernetes is an overkill. And the way that I see it, everyone wants to use this shiny technology, but they rarely stop to ask if they actually need that complexity. Do they even have the team to manage Kubernetes platforms? And you have to think from first principles and break down whether you actually need to use Kubernetes, because when I'm working with startups, I consistently see teams wasting months of engineering time setting up and managing Kubernetes clusters. And these teams often have fewer than 10 engineers and a product serving maybe a few thousand users. Now, what these companies really need is just simplicity and speed. Because when you're just starting out, you need to focus your limited engineering resources on your core product and not maintaining complex infrastructure. And that's where AWS's ECS service comes in. It offers a much simpler approach to container orchestration and is incredibly powerful. It just hits the sweet spot for so many businesses by providing the key orchestration features that you need without the complexity of Kubernetes. Now that you understand the core fundamentals of Docker, you have to start building and implementing your newfound knowledge. And I recommend heading over to Docker Docs. You'll learn how to actually run your first container and push your first image, and it's beginner friendly and it'll only take you about 15 minutes. But that's not going to be enough if you want to land a job in this industry, because in 2025, every engineer needs cloud skills in order to stand out. And I've just released a step-by-step roadmap on everything that you need to know, so just click right here to watch it.